Good day, everyone. Today, I will briefly present our research title, Image-Based Classification of Golden Melon Ripeness using Convolutional Neural Networks and Data Augmentation. Our work aims to develop a reliable, non-destructive method to determine melon maturity using image analysis. In the next 5 minutes, I will cover 5 main points of our research. First, the importance of ripeness detection, our key contributions, the methodology, the comparative results, and finally, the impacts of our findings. Okay, melon is a high-value crop in Indonesia, widely distributed domestically and exported internationally. Because of melon continued ripening after harvest, accurate timing is essential. Too early, reduce sweetness. Too late, reduce shelf life. Most previous studies used different melon varieties, mainly net melon and applied coarse label, like unripe and ripe, only binary class classification. Golden Apollo melon, which has smooth skin, has not been extensively researched. The most recent work by Augusta and Usman achieved an accuracy of only around 65%. In addition, there is also no dedicated public data set available for this melon variety. This creates a clear research gap, especially for classification based on days after planting, which is the standard used by melon farmers. Our contribution addressed these gaps. We construct a new curated dataset of 230 controlled condition images. We developed models for distinct day after planting maturity classes, including 47, 53, 60, and 67 days after planting. We also did comparative evaluation for 4 scenarios. The first scenario is principal component analysis with SVM. The second one, PCA with neural network, CNN without augmentation, and the last one is CNN with augmentation. In this research, also we obtained clear evidence that CNN spatial feature learning outperforms PCA-based feature reduction. Our workflow includes images pre-processing through resizing and normalization. For the traditional models, PCA reduce each image to 100 principal components before classification. For the deep learning approach, a CNN is trained directly on raw images. We also introduce data augmentation, rotation, shift, zoom, and flipping, performed on the fly to improve generalization. All models were trained for 50 epochs using the same train test split. 2 of thirds are training and 1 of third as testing data. For matrix performance was evaluated using accuracy, precision, recall, F1 score, and confusion matrix. Here are the key findings. From experiments, the CNN with data augmentation achieved the best performance with 86 accuracy and obtain F1 score of 0.87. Even the CNN without augmentation outperforms traditional models, achieving 78% accuracy. In contrast, PCA and SVM achieved only 72% accuracy, and PCA with neural networks had the lowest accuracy at 64%. The main reason for this gap is that PCA compress spatial information, making adjacent day after planting classes, especially for 60 day after planting. It is hard to separate with PCA. CNNs, on the other hand, successfully learn texture and color variation that represent ripening transition. As a conclusion, the summarized deep learning methods, especially convolutional neural network with augmentation, provide the most reliable approach for classifying golden melon ripeness. Our created dataset enables fine-grained analysis that has not been done previously for this variety. In the future, this work can be extended into multimodal system using image and acoustic data and integrated with YOLO-based detection for real-time in-field maturity monitoring. This contributes to more accurate harvest planning, improved supply chain consistency, and smarter precision agriculture tools. Okay, thank you for your attention.